Good morning. Here we are back with the second portion, the later portion of Chapter 19. On the previous lecture, what we had done is we had gone through and looked at ways of determining how much energy the molecules have, and then we had looked at specific heats, latent heats, and then we had moved on to these thermodynamic processes. And what the thermodynamic processes are looking at are, in addition to the heat that's coming in or leaving the system, we're starting to include work. And so if we have a sample, so here we've got this cylinder, we've got a movable piston, and a surface in here that allows us to go in and change the volume. We can have energy transfers take place if I push this down. If I push this area down, that's going to transfer energy into my sample. If I allow the sample to push that away from it, that will transfer energy out. And it is just like Physics 4a back when we pushed on an object over a displacement, and we would transfer energy. We could determine how much energy was transferred during that force applied through that displacement. So anyway, we now have a formula for work that we started from our Physics 4a formula and developed PDV. So now we have a formula that allows us to go in and calculate work. And we had looked at this example. I'm reviewing a bit from last time. So this is the integral that we have set up now. And what we're looking at is a process where the pressure is not constant. So if the pressure is not constant, then we've got to be able to find a way to carry out that integration. And we said that for an isothermal process, the way we could solve this integral is to realize that for an ideal gas formula, the pressure could be replaced by nRT over V. So I did that. I replaced the nRT over V. The nRT are all constants because it's an isothermal process. So the T is constant for this process. That leaves us with dV over V, and carrying out the integration gives us a natural logarithm of VB over VA. So there's an example of calculating a formula for the work. Now, what we had also talked about last time is that if we follow a different path, we'll have a different amount of work. If we push more forcefully, if the sample of molecules push more forcefully with more pressure, or if we push on the gas molecules with more pressure, compressing them, if the pressure is higher, we're going to have more work, even though it's the same volume change. And so we can see that here in going from A to B along the isothermal process. The area under the curve, what we saw in the formula on the previous page, is larger. There's more work. There's more energy transfer that takes place through the isothermal process than if we did an isovolume and then an isopressure process. So if I can find a way to get more area under the curve, that's going to be more work, and that's useful, we'll find, for designing heat engines, so refrigerators, things like that depend on these thermodynamic cycles. So there's a lot of really interesting applications coming up. So I think we had gotten as far as this, and then we kind of ran out of time. But what this is showing is just conceptually, same idea, that if I follow a path from A to B versus A to C, even though we've had the same amount of volume increase, see how B and C represent the same amount of volume, because this occurred at a higher pressure, on average, there's going to be more work, more energy transfer through the isothermal process than it is in the adiabatic process. All right, here's an example, 1910, first law used in isobaric and isovolumetric process. So this is kind of like what we saw before. It's similar. Now we've got some actual numbers that are put in. Let's see what we've got here. So this is a little weird. Sorry about this. But I should have changed I could have done that. I could have edited this. This they're calling point B, goes to point D, goes to point A. I should have changed it to ABC. Anyway, that's the direction we're going here. So we're actually going to start something that starts at 10 liters of volume and at 2 atmospheres. So this is 2 atmospheres right here. 2, 4, 6, 8. Looks like this is probably 10 atmospheres, but they haven't labeled it. So it's going to compress the gas first in a way where the pressure is maintained, and then it's going to increase the pressure. Now probably that means taking heat out, lowering the temperature, and then here would be raising the temperature. Notice that going from B directly to A, that would be maintaining the same pressure, same temperature the whole time. But as we remember those hyperbolas, those isotherms. So as we move this direction, we move towards higher temperature, and as we move through the isotherms in this way, it's towards lower temperature. So anyway, that's what we've got here. And what is it they have us calculating here? So they want to calculate the work, and they want to calculate heat. Perfect. So this is the kind of stuff we want to do. So again, all those heat engines and refrigerators and heat pumps and things, they depend on these thermodynamic processes. Let's see how this works. So B to D to A, and what we've been told is that the pressure at point D is 2 atmospheres. Now, we want to work in standard units. We don't want to be working with liters and atmospheres. We want to be working with pascals and cubic meters. So I change the pressure and the volume into pressure into pascals, volume into cubic meters. I've got this on my PV diagram, and notice that A and B, well, we got to find out if that's at the same temperature or not. We will find that out. So this is the starting stuff. Now in the problem, they didn't tell us how large the sample was, and I thought the example would be more useful for you guys, and you'd be able to see more of what's going on if we just put in a sample size. So I picked 1 mole. Now that's dangerous because you can't assume there's always 1 mole. They just didn't give a sample size, so that's what I'm going with. So anyway, I'm going to say that there's 1 mole. And then I put in the ideal gas formula. So now I'm calculating the temperature. So if this is the pressure and volume, and if there's 1 mole, then the temperature is actually at 244 Kelvin. So it's already at a pretty low temperature here, right? We've got something that's at a really low temperature, 244 kelvins. Now, what we want to do then is, I kind of wanted to go around and just find the pressure and volume at each of these points. Now, I know what the volumes are at B and D and at A. I know all the volumes. The pressures, I know the pressures at B and D, but we should verify the pressure at point A, find out what that is. And I'd like to find out what the temperatures are at D and at A. So to do that, I've used ratios. Now with the ideal gas law, you can just put the ideal gas law, write it out, put in the knowns and solve for the unknown. Another way to solve for the ideal gas law is to use a ratio approach. So if I'm going from B to D, for example, what I could do is say, hey, when I get to point D, the ideal gas law applies. Back at point B, the ideal gas law applies. So what I could do is I could write those 2 formulas down and then take their ratios. Now the idea of taking ratios is a lot of times we can get a lot of things to cancel out. And that can be really handy. So notice that by taking the pressure, volume, and RT, well, let's see what things we can get to cancel out here. The pressures are the same at D and at B, so the pressures cancel. The number of moles is the same, cancels. The gas constant, big R, always cancels with big R, it's just a constant. So I've been able to write a ratio of volumes and a ratio of temperatures. So I solve for temperature at D and put all the numbers in. Now when I use the ratio, I can actually go back and use liters, for example, right? I can go back and liters over liters will work. Atmospheres over atmospheres, the units will cancel. Now, kelvins and Celsius aren't the same thing. Ratios in terms of kelvins are not the same thing as ratios, so that would still need to be in kelvins. But notice that the temperature that I got, 49 Kelvin, that's a really chilly spot on our PV diagram. Okay, but anyway, we've been able to use the ideal gas law to determine what the pressures and temperatures are. Again, I did this one more time. Here I went from, I compared point A and point B. So down here lower, I compared these. I wrote down the ideal gas law for point A, wrote down the ideal gas law for point B, and canceled out all the stuff that was constant. Now, n's are going to cancel, r's are going to cancel, the t's are going to cancel, and so I'm left with 1 on this side. Remember, there's still a factor of 1 over on that side, and so I can solve for PA. And so the pressure up here at point A is 10 atmospheres. So now I know the pressure, the volume, the temperature at everywhere, at each of those 3 points. Okay, and in fact I made a table. I think this is so useful. So I made a table, point B, point D, point A. I've got all the temps, I got the volumes, and I have the pressures. Now these are not standard units, but I can convert back into standard units as needed. But I just got that table up. Okay, now I like these drawings. I've used these a couple times before. I just draw a picture of my sample. I allow for a variable volume, so I put a little piston in there that can be lowered or raised. And then I ask, what's heat doing? Is heat going in? Is heat coming out? Or is Q equal to 0? Same thing with the compression. Am I putting energy in through compressing? Is energy coming out through expansion? Or is work 0? Now, on the, I gotta go back and take a look at this diagram, The process from B to D. So let's go back and look at that real quick. B to D was a constant pressure process. Okay, so if I'm operating here, there is a compression that's taking place. If there's a compression taking place, energy is coming into the sample due to that compression, and we call it work. So there is work being done. Now, since it was constant pressure, the work formula can be written as P delta V. This is my pressure in pascals. This is the decrease in the volume due to the compression. And that says we are at negative 1620 joules. Now the minus and plus signs are a little confusing here. The way work is defined, and this seems backwards, but when energy is leaving the sample due to work, they call that positive. And when energy is coming in to the sample due to work, they call that negative. Now it still kind of seems backwards to me. So that's why I draw these diagrams. So I kind of ignore the sign here. I mean, I wrote it down officially, but I'm kind of ignoring that and just thinking, okay, 1620 joules are coming in due to the compression that took place. Now, that was for the process BD. How much work is done in the second part of the process? They want us to get the total work. So let's go back and look. So this part of the process, the work is this area under the curve, and we've got that 1620 joules. And then this part of the process, D back to point A, is 0. The volume wasn't changed during that second process. If the volume remains fixed, W is equal to 0. So, taking a look at our diagrams here, first process, energy came in due to work, 1620 joules. Second process, W is 0. Okay, the volume remained fixed. That says that the total work done through those two steps combined was 1620 joules, and it was 1620 joules coming into the sample. That's going into those molecules inside the container. All right, so let's see what's happening to the internal energy. So when I'm doing a problem like this, looking at these thermodynamic processes, I'm thinking the two easiest things to look at, I'm going to say, is the internal energy. In fact, I usually go to the internal energy first, and the work. There's a set of reliable formulas for work. There's a set of reliable formulas for the internal energy. Now there's also kind of a set of reliable formulas for Q, but to me, for whatever reason, I tend to think of internal energy as the most important item, and then I go for work, and then I go for Q. All right, so for the internal energy, now I'm going to assume for the problem, I'm going to add a couple things. I'm not really assuming so much as just placing something in there, saying I want to ask more questions, and so I need a few more pieces of information. I'm going to say that the gas is monatomic. Maybe it's helium, maybe it's neon, but I'm just going to pick. I could pick monatomic or diatomic. I'm going to go with monatomic. So if it's monatomic, then the internal energy can always be calculated by 3/2 nR delta T. Always. Every process. Doesn't matter what the process is. I just need to find out the delta T. What was the temperature I started with? What was the temperature I ended up with? If I know those, I can calculate the internal energy changes for a monatomic or a diatomic gas very easily. So 3/2 nR delta T, and I can look up here for the delta T's. And what that told me is that in the process from B to D, the molecules lost 2,430 joules. Okay, so that's the keeping track of that. That's going to determine how much the temperature drops, right? The molecules themselves lost that much energy. Now, when I go from D to A, same formula, but I have a different delta T. Notice the delta T is just reverse. I dropped 195 kelvins, and then I went up 195 kelvins. And so going from that second process took me right back up so that the net internal energy difference is 0. Again, looking at that process before. If I had followed the isotherm, temperature would have stayed the same all the way through. The internal energy would have stayed the same all the way through the process. Instead, we imagine doing this process where the internal energy really dropped. Temperature really plummeted. But then we did a second process that brought the temperature back, and it brought back all that internal energy. So temperature and internal energy are proportional to each other. Now that I've got the work and the internal energies calculated, I can calculate the heats. And so the heat for the process, as we had suggested, the heat, we're going to lose 4,050 joules. I combined the internal energy information and the work information to find out what the Q was. Now the plus sign here, again, it's a little weird that we define it backwards, but that is the formula that we work from. So anyway, we've got everything calculated. We calculated the works, calculated the heats, calculated the changes in internal energy. Okay, here's kind of a guide for some of the processes. If we're an isothermal process, then T is constant. If T is constant, then delta T is 0 and internal energy is 0, and that means Q equals W. Any heat that comes in must be lost, or any work that comes in must be lost. For the isobaric, the pressure is constant, and so in this case, the Q can be calculated. Changes in internal energy plus W, the work can be written as pressure delta V. If we have a constant volume, anytime the volume is constant, the work is going to be 0. And so any changes in internal energy are going to come from heating. Okay. And then the adiabat's Q is equal to 0, and that says that any changes in internal energy are due to expansions. And again, this is kind of a frustrating minus sign. Work is the quantity that's kind of defined backwards from the way you might think it should be defined. Okay, now when we look at ideal gases, it turns out that for different processes, the Q's are different. Okay, depending on what type of a process we're operating with, the Q formulas are going to be different, and that means that we need to define separate specific heats if the process is constant volume compared with if it's constant pressure. See how that works. Now these are what are called molar specific heats. They're keeping track of how many moles we have in our sample, and that actually makes a lot of sense, right? Molar specific heat probably makes more sense than gram specific heat. And so here are the formulas that we have here. If we're operating at a constant volume, then the internal energy, internal energy is always given by 3/2 nRT for a monatomic, 5/2 nR delta T for diatomic. The Q for a constant volume process will be equal to those numbers. And so here's the diagram. Any Q that comes in, that's what shows up as delta E, because there's no work if it's constant volume. Now at constant pressure, a different thing happens. Constant volume means that this container is rigid. I heat it up, I just keep heating it up, but it never expands, and so all the heat that goes into internal energy. But what happens if I have a flexible container, one where the top can move? Well, as I heat it up, pressure goes up and that top begins to expand. And that means that we're going to lose energy due to work. So under constant pressure, I put Q in, the material expands, and so some of that energy is lost. And that means that when I'm heating something up, when I'm trying to increase its temperature, and temperature is going to be related to the internal energy, I have to put extra heat in. If the material is able to expand, it's going to lose energy along the way, and I have to put extra energy in. We can calculate how much. The Q that we have to put in is equal to the increase in internal energy, plus I have to put in an amount of Q to compensate for how much work is lost. Now the work for a constant pressure process is P delta V, and the ideal gas law tells us that for constant pressure, P delta V is equal to nR delta T, if P is staying constant in the ideal gas law. So what that leads us to is that for a monatomic gas, I've got to put in enough Q to create the increase in temperature, to increase the internal energy. But I also have to put in an additional nR delta T to compensate for the energy being lost in the expansion. So what that says is 3/2 plus 1 is going to give me 5/2. Now that's monatomic. What happens in the diatomic case? Well, in the diatomic case, I'm going to have 5/2 nR delta T, plus I'm still going to have that nR delta T portion. So if we combine all those things together, what we find is that for monatomic gases, if we run a constant volume process, then the molar specific heat is 3/2 R, and the there's a V right here. Okay, add that in. And then for the diatomic case, it will be 5/2. If we move on to constant pressure processes, the ones down below, the molar specific heat at constant pressure is 5/2 R, and the diatomic at constant pressure is 7/2. Those are the numbers. I just plugged the numbers in to show what values these would be for the different types of gases. So 12.5 joules, 12.5, 20.8, and 29.1 is what the theoretical, this theoretical approach is predicting. And then what we can do is we can compare it with a chart. Now the chart from the book, again, the author's going back to using calories. This should be in joules. If this were converted into joules, we would see these numbers matching up with the values that we saw on our example. Okay, so that's it. That's how this works. Okay, kind of a repeat of some of the things that we've looked at here. So for a gas in a constant volume process, things to keep track of. No work is done, and the heat that we put in will all show up as internal energy. If we're operating at constant pressure, we not only have to compensate for the internal energy, but we have to include the P delta V. Okay, and then another formula down here that I'm not terribly useful. All right, so here we're looking at more complicated gas molecules. We talked about this a bit, that molecules can have rotational energies, so here are the rotational pictures. And then there are vibrational energies. Now, the vibration that's taking place indicates a change in the distance between two nuclei in a chemical bond. So if I've got a chemical bond, say carbon and oxygen or something, there's vibration that takes place as the nuclei vibrate back and forth. If it's diatomic, there's just that one axis along which the nuclei can vibrate back and forth. Okay, ooh, I went back instead of forward. Now, another thing to keep track of here is something called the equipartition model or theorem. And the idea here is that for different sorts of materials, we can determine, we can predict what the specific heats will be based on what kind of energies they will have. And so just motion from one place to the next is referred to as translational energy. And since for translation there's x, y, and z directions, that would give us 3/2 kT. So there's a 1/2 kT for each what they're calling a degree of freedom. So what that really means, a degree of freedom is an axis along which some kind of motion could happen. So for translation, that's just Vx, Vy, and Vz. Now, rotation for a diatomic, so it gets more complicated with more complicated molecules. But if I have a diatomic gas, then rotation for a diatomic allows us to think in terms of two axes of rotation. So if I've got something that's rotating, if I've got a molecule that's along an axis, if I have a nucleus here and here, rotations along the axis passing through the nucleus doesn't really indicate any rotational inertia. And so one of the axes is excluded. There's only two axes of rotation. So we refer to that as 2 times 1/2 kT. And then vibrational kinetic energies really don't kick in until you get up to really high temperatures. For most gases, you have to go up into the thousands of kelvins before the gas molecules have appreciable vibrational energy. Now that's not true for solids. A block of iron, for example, at room temperature, its internal energy is almost entirely vibrational. So for a block of iron or something, plenty of vibrational energy, but gas molecules don't pick that up until we get to higher temperatures. So we just kind of leave that out. We put that in our diagrams, but then we remind ourselves we're really working in this range, kind of between 100 Kelvin, it's not a linear scale here, up to 1,000 Kelvin. And in that range, the translation and rotational energies are the ones that we have to keep track of. Now, as I was saying, if you look at solid materials, especially metals with fairly simple structures to them, crystal structures, we can show that each nucleus, these are vibrational quantum states, each nucleus in a block of some metal is able to vibrate back and forth. And when we calculate how much energy there is of vibration in each direction, that corresponds to a full value of R in each direction. So specific heats for solids, once you get past a few hundred Kelvin, once those quantum states are populated, kind of levels off at 3R. A lot of materials, a lot of metal samples have a specific heat of 3 times R, or 6 1/2 kTs worth of energy. So And we'll see this in some of the examples that we look at. Well, we'll see this in lab. So in lab, when we look at the specific heats of some metal samples, we will be looking at molar specific heats as well and comparing them to this theoretical amount. Okay, so let's talk a little bit about adiabats. Adiabats are a little more complicated. If the pressure is constant, you know, the formulas were pretty straightforward. When the temperature was constant, we had those isotherms. When the volume was constant, those processes were pretty straightforward. Adiabat derivations are a little more complicated. Now, I'm not going to go all the way through the adiabatic derivation here. The book goes through it. The slides here that go along with the textbook make an attempt. So I'm going to skip this and say, don't worry about their derivation. In fact, I have a formula that will apply in more situations than the one in the book. So there's kind of a super adiabat formula we'll use here in just a minute. But in order to introduce adiabats, let's take a look at this diagram. Again, it's a two-step process. This time it goes ABC. So they actually followed the alphabet this time. So that will make it easier. And point A is starting with 1 cubic meter of some gas. And they tell us it's behaving ideally. So yes, it's a gas that's going to follow the ideal gas law. And it's monatomic. So that we're going to need. Now there's a process from A to B that's adiabatic. And that takes us from 100 kilopascals, you know, somewhere around 1 atmosphere, up to 200 kilopascals, somewhere around 2 atmospheres. And then it takes us to point C. What they want us to do here is calculate everything, okay? And that's pretty typical for these thermodynamics kind of problems, is what they do is they give you some starting information, and then they say fill in the rest. So on this problem, what we want to fill in, we want to get all the temperatures, we want to get all the pressures, we want to get all the volumes, and then we want to get all the W's, all the work, and we want to get the Q's, and we want to get all the delta E's. So we better get to work here. Let's see what we got. This might take a little doing. So first of all, there's an adiabatic compression. The volume decreases along an adiabatic path, and then we switch and we continue the compression, but this time it's isothermal. So we'll kind of compare which formulas are getting used for each one. So it's a gas. We're going to treat it as following the ideal gas law. It's monatomic, so it's helium, neon, argon, or krypton most likely. The starting pressure, volume, and temperatures were all given. So I'm just going to write those down. Right, so that's good. We're starting to write down what was given. Now, since I know all this, I can calculate the sample size in terms of numbers of moles. I ended up with about 40 moles, 40.09. And so I stored that in my calculator, so when I come back, I won't be rounding. You don't really want to round to 40. I'm going to keep a couple extra significant figures here. All right. The other thing that I want to keep track of, because it turns out we need this for the adiabatic process, I need to know what the molar specific heats are for the gas sample. So the molar specific heats are going to be 3/2 R and 5/2 R, and that's because it's monatomic. If this had been diatomic, this would be 5/2 and this would be 7/2. But 3/2 and 5/2 is what we're going to work from here. Okay, let's see how adiabats work. And here it is. I should have circled this and put fireworks around it. That is the super adiabat formula. What the super adiabat formula does for us is it allows us to relate pressures ratios, temperature ratios, and volume ratios between the two endpoints. So if we go back to, here's point A and here's point B, and that's the adiabat. What I can do now is I know all the numbers at point A. What I can do then is I can use this formula to solve for the pressure at point B. Actually, that was given. The volume at point B and the temperature at point B. So I did need one more piece of information at point B, and they gave us the pressure. So I know the starting pressure and the pressure at point B. It's a ratio of 2, and since the super adiabat formula is in terms of ratios, I am going to solve for TB. So I'm going to solve for TB over TA and relate that to the pressures. Now, currently this is 1 over the CP, 1 over the CV. These are the molar specific heats. I actually need those. And then 1 over R. Now what happens whenever you're doing these calculations, let's say we're solving for temperature, I can exponentiate this by a factor of R, which cancels the 1 over R, and that R then will show up over here. I can also invert the ratios and the formulas will still work. So it's a good opportunity to go back and practice some of your algebra skills, remembering how exponentiation works. Anyway, I've got this ratio of temperatures equal to the ratio of pressures to the R over CP. Now, since CP is 5/2 R, CP over R is 5/2, but that's the inverse. So I've got to write that as 2/5. So it says the ratio of temperature differences between point A and B is going to be 1.32, and that says the temperature is going to be 396. We started at 300 Kelvin. By the time I get to point B, we're at 396. Temperature went up. Okay. Now, I'm going to do the same thing using my super adiabat formula to come up with volume. So I can do the same thing. I can relate the volume ratio to the pressure ratio, which I know, and I solved that for VB and carried out all the calculus. Again, this time I ended up with CV over CP as an exponent, and CV over CP is 3/5, and I ended up with a volume of 0.660 cubic meters. So check the algebra. Again, it's a good chance to go back and practice your exponentiation. We are not through. We only did the adiabat process. In fact, the adiabat process is still continuing. So here is the adiabat process. Q is equal to 0. I can go in and I can calculate delta E as 3/2 nRT, delta T. So I've got my two temperatures now. Once I get all the temperatures, I can calculate all the delta E's, right? So plugging everything in, there's my number of moles. I ended up with the increase in internal energy was 48,000 joules. Now, I know it's an adiabat, so none of that came from Q. It must have all come from the compression. And here's my picture. So Q was 0, it's an adiabat. I calculated that the internal energy went up by 48,000 joules. I knew that from the temperature and the fact that it was monatomic. And that means that the compression must have placed 48,000 joules into that sample. Okay, we pushed on the sample, transferred that energy in. Now let's move on to the isotherm. So we calculated everything on the adiabat. Well, it's an isotherm, first of all, so Tc is equal to Tb. That's 396. That wasn't too hard. Since it's an isotherm, the internal energy increase is going to be 0. So I think the adiabats are harder. The isotherm calculation should be a little easier. Now, they did tell us that the volume here is 1/2 a cubic meter. So I used our old ratio trick and used that to determine that the pressure at point C is 264 kilopascal. So we could go back. I don't think I did a final table of everything, but we now have the temperatures, the volumes, and the pressures at points A, B, and C. Now, for the energy transferred through work, this is an isotherm, so we've done this calculation, or this derivation before. So here's our derivation for the work, and this time I ended up with 36,300, I guess this officially was supposed to be negative. Again, the plus minus signs on the work are backwards. This comes out negative, which means work came in. Since it's isothermal and the internal energy was not affected, it must be that if 36,000 joules came in, 36,000 joules were lost due to heat. So kind of the way you think of this is here's the sample, we compress it, it begins to heat up, but as it heats up it loses that energy to the environment. So at the end of the day, it's still at the same temperature it started at. All right, a lot of good stuff to look at in this example. You've got two different processes, kind of an example of going in and calculating everything. All right, so that takes us through kind of operating with these different thermodynamic processes. We've got all that stuff in place. We are ready now to come back, and in chapter 20, we're going to come back and apply a lot of that stuff. Let me go back and take one more look at this. We're going to come back and apply a lot of these processes. Again, looking at things like heat engines and looking at refrigerators to see how we can cool things down or heat things up or generate a lot of work, a lot of mechanical energy from that. Okay, so let's move on to kind of the last set of topics in the chapter, and these are, this is referred to as heat transfer. What are the ways that heat actually does get transferred into a sample? Up until now, we've kind of treated it as if I take my sample, I put it in a container, and I heat it up. And heat it up means putting it in contact with something at a higher temperature. Now, there's different ways that we can heat things up, so let's take a look and see how that works. There's a process of conduction. So when we say something is being heated through conduction, that means that, you know, two samples are directly in contact with each other, and that the molecular motion from one ends up getting transferred to molecular motion in the other sample. If I put something on a range top, stove top, you know, I boil some water or something, typically there's going to be a burner or a heating element of some sort that heats up the pan. And so the pan can heat up, and then once those molecules, so what it is there's a heating element, we turn on the electricity, and the molecules in there have vibrational energy now. They're going to higher temperature, they have more and more vibrational energy. I put a pan in contact with that through conduction. The heating element transfers some of that energy into the material of the pan, and then as those molecules are moving faster, there's water inside my pan, then the water molecules begin to get jostled by the vibration of the molecules in the pan. So all of this is conduction. It's going from flowing through the material from kind of molecule to molecule. Now, there's other types of energy transfer here, convection and radiation, and we'll get a chance to come in and talk about those also. So we're going to write this down. Let's for conduction. When two materials are in direct contact with each other, so here's a region at a higher temperature, here's a region at a lower temperature, and they don't show this actually directly in contact. What they show is heat is going to conduct through this intermediate material. So we're interested in the intermediate material. The materials on the sides are kind of thought of as heat reservoirs or temperature, uniform temperature regions. And we're specifically focusing on this region where the temperature varies. So there's a temperature gradient between the two. And we're going to say that the temperature gradient exists along some length L, and there's going to be a cross-sectional area through which the heat can be transferred. Now back in this formula, I guess we got to look at the formula. Notice that the delta Q delta T, that's a heat rate or an energy rate. So that's telling us what's the rate at which energy is leaving this side, and what's the rate at which energy is arriving here. Notice that this energy rate is the same all the way through that intermediate material. Once I've reached kind of an equilibrium situation, where there's a steady flow of heat through that material, this value would be the same through that entire region. So what it depends on is this. It depends on the cross-sectional area. If I have a bigger contact area, there's more room for the heat to transfer, for the molecules to run into each other. So if I'm thinking of a house with a window, and I'm concerned about the heat loss through a window, if the window's twice as big, that's twice as much area. That's twice as much heat loss that we would expect. So again, if this is thinking of heat, the rate at which it's flowing, this is going to be like in joules per second. That's going to be some number of watts. And if I have energy leaving at some rate, some number of watts, I'm going to need a heater with the same number of watts to replace the heat. If I want, the inside of the house to stay pleasant, warm, then I'm going to have to compensate for this loss. So it depends on the cross-sectional area. It depends on the temperature gradient. Now this reduces down to just the difference in temperature between, say, inside and outside. So if I got a material, again, if it's a window in my house, there's a temperature inside and there's a temperature outside, and that's going to help determine the rate at which energy loss is taking place here. And then it depends on the thickness. So if I make this material thicker, it's a longer path for the energy transfer to take place, and the energy drops off. It's inversely proportional to the thickness of, if it's a window, it's the thickness of the glass. So that's kind of what we're looking at here. Now, here are, one more, sorry. And then out front, little k is the thermal conductivity. Now, we haven't used little k for anything else, have we? And it does seem like in physics and engineering too, to some extent, when in doubt, we just use k for everything, right? Let's see, have we defined k for anything else? Well, in physics 4a, we defined that for a spring constant. This is not the spring constant. And then already here in physics 4b, we have defined little k as Boltzmann's constant. Well, this is certainly not, it's not Boltzmann's constant. This is a conduction formula, and it's actually a material property. So it's the thermal conductivity of the material, and here's a table. So the constant little k is called the thermal conductivity, and it's got a lot of units to it. So the units here, I'm not going to look at the calories, joules per second, per meter, per degree Celsius. So materials with a large value of K are good thermal conductors. They will readily allow heat to conduct through the material. With small k, those are considered to be insulators. So for example, if you're walking through the park and it's a cold winter day, it's freezing outside, and there's a wood bench and there's an aluminum bench, which bench are you going to sit on? You're going to sit on the wood bench, right? Because wood is a good thermal insulator, and you know that if the bench is freezing, because it's freezing outside, that you don't want the bench to draw all that thermal energy away from you. You would rather sit on a thermal insulator like wood, where, let's see if the numbers, wood's, I don't see it. Aluminum's certainly on there. That's got some, yeah. So these metals, silver, copper, aluminum, and steel to some extent, are really good thermal conductors. And so I don't want to sit on the aluminum bench. Similarly, in the summer, you're walking through the park and there's a wood bench and there's an aluminum bench there, and the sun's beating down and it's 100 degrees outside. Which bench do you want to sit on? You still want to sit on the wood bench, right? For the same reason, if you sit on the aluminum bench now, it's at this really high temperature. It's going to transfer all this energy into you. It's going to be really hot. So I guess park benches, you want to use insulating material, right? So that you don't run into those problems. All right, so we've got these metals with really high thermal conductivities to them. And then we have some intermediate kind of building materials here: glass, brick, concrete, water. And then we've got some stuff that's really good insulating. Fiberglass gets used in construction a lot because it has such low conductivity properties to it, and because it, when placed in the walls or the ceilings of buildings, it slows down the flow of air also within that space. So, you know, there are the different list of materials. Now, let's take a look at an example here, a numerical example. We keep talking about a window in a house, and look, here is the window in the house. So it says heat loss through windows. So here's a window. It's a big window. It's like 2 meters by 1.5. It's a good, yeah, it's a good sized window. So it's a pretty good sized window. It's 3 square meters of area, and it's 3.2 millimeters thick. Now, you know, if you look at windows in buildings now, they're double paned, and they're double paned with some kind of insulating material placed between, something like argon. And so those are requirements. Windows are really large sources of energy loss when you're trying to heat a building. And so, anyway, this window is only 3.2 millimeters. Yeah, I guess that's how thick the window is. It's, and then the temperature at the inner. So, fortunately, this is pretty funny too. This is a window on a house. Look, it's 14 Celsius outside, and we want to keep the house at 15 Celsius. What? 15 Celsius is cold. I think they might have made an error here. I should have changed this 15 to 25. 25 would have been a much better number to work from. Anyway, they just left a 1 degree difference, so it's not much of a temperature gradient. But let's go in and calculate what we've got here. So I'm just taking the formula. I wrote down the thermal conductivity for glass. I wrote down all of its units. Here is the area of that window. Here's how thick it is. And the temperature difference is only 1 Celsius. Not much at all. Now, putting all these numbers together, I ended up with almost 800 joules per second of heat loss in that building. And I tried this a couple times. This is what I got. If I made a mistake, you guys let me know. But the window is not very thick, is what seemed to be, and the window's pretty big, which seemed to be driving the numbers up. And but the delta T is so small. Still 800 watts. So here's my house. Here's my just one of the windows. That's 3 square meters, and I have to get an electric heater and plug it in. That has 788 watts. Just to compensate for the heat being lost by that one window. So that's quite a bit, right? Space heaters all over the house, each one trying to compensate for heat losses through the windows for that room. In industry, often instead of using thermal conductivity, what we do is we take L divided by K for the material. So it's kind of what are the material properties and how thick is it? And we call it the R value. So if you go to, you know, a Home Depot or Lowe's or something and you're looking for insulation, they're listed in terms of R value. And when we remodeled this room here, I think the walls are all R13. The ceiling is like R50 or something. It got some really thick bats of insulation, and it works pretty well. This room stays pretty well insulated. So you can see the fiberglass insulation. This is saying 4 inches of fiberglass. It has an R value of about 12, and I'm thinking it's 13, but maybe it is 12 that you see in the home stores. Anyway, that's an R value. Now R values are written in a way where the bigger the R value, the better, right? So the big R value, since it's the inverse of the thermal conductivity. All right, now there's another way that we can get heat moving around, and it's called convection. So remember, we just talked about conduction. Convection means that rather than waiting for heat, like in a sample of water, to travel around, what you can do is you can move the water from one location to another. I always think of, you get in the bathtub and it's a little chilly, so you turn in some hot water, but the hot water only goes to your feet, right? And I go, well, my feet are really warm right now, but the rest of the water, and you go, how could I solve this problem? You go, oh, convection, just swish the water around, right? So it does take some time for the thermal energy to transfer through a material, and if it's water, you just swish the water around. Now, if you're heating something, here's my pan, and it's over some kind of a burner. Often you'll end up with convection currents automatically. So what happens when you're heating something up in a pan is that often the water at the center of the pan heats up the most and becomes less dense. And so when it becomes less dense, it begins to raise up, and then water comes and circulates down along the sides. So you can end up with circulation patterns inside. Another, I guess you could reverse this. If you heated up the sides, then you would have water from the sides, and it would be dropping down through the center. So some of these things happen automatically. Here's a house with a furnace. Now here we're actually going to pump the hot water. So the furnace is going to heat the water, and then if we pump hot water through to the radiators within the house, then the radiators heat up, and that becomes our third method. The radiators actually radiate heat. And so we also want to talk about radiators and look at a couple of examples with those. But convection is, if you've heard of convection ovens that cook faster, a convection oven, in addition to the burners that are inside, there's a fan, there's an additional burner, and there's a fan that circulates the heated air through the oven. So a fan just keeps the air going through, and that means that the heat's going to be transferred more efficiently. All right, let's take a look at radiation. Now, it starts off by saying radiation is the form of energy we receive from the sun. That's true. So the sun generates a bunch of light, and that light is across the spectrum. So not only is there visible light coming in from the sun, there's infrared, there is ultraviolet, there's a little bit of X-ray and gamma that are produced, mostly blocked by the atmosphere. There's radio, so there's a whole spectrum of this light. Now, it doesn't, you don't have to have a star that's at thousands of Kelvin to radiate. These radiators are radiating. So those radiators are at a temperature where they're going to be able to radiate in the infrared. An infrared feels pretty good on a cold day, right? Maybe you've gone shopping at a store where when you walk in, there's this warm blast of air, and well, it's not necessarily a blast of air, I guess. It's just a sudden sense of warmth, and you look up and there are all these infrared discs or dishes that are radiating infrared, and that's light. Those are photons of light that transfer from some kind of a source, and you can absorb those. And when you absorb those, you absorb the energy, and temperatures go up. So radiation is actually pretty interesting, pretty important. Now, our formula for radiative effects is this. Here is the rate of energy coming off due to radiation. Now, it depends on how reflective or how absorbing a material is. If something is totally reflective, completely shiny, it doesn't absorb light. It also doesn't radiate light. It turns out that absorbing light and radiating light go hand in hand. If you're a good absorber, you're good at radiating. And if you're really bad at absorbing light, you're really bad at radiating light. So that is a factor we call the emissivity. And the emissivity is somewhere between 0 and 1. So 1 is 100% totally absorbing, and 0 is 100% totally reflecting. Now, the next constant here is called the Stefan-Boltzmann constant. It's just going to make all the units match up. This is the surface area. So if I've got twice as much surface area, we'll radiate twice as much energy. And then finally, this is kind of interesting, the rate at which energy comes off, the rate at which light energy radiates away from an object like the sun or like a radiator depends on temperature to the fourth power. So as you go to higher and higher temperatures, you radiate more and more energy. Now here's the Stefan-Boltzmann constant that we looked at. That's its numerical value. It's 5.67, 10 to the minus 8 watts per square meter per Kelvin to the fourth. I should have covered up that period. I didn't get that edited out. The emissivity is a number between 0 and 1, just as what we were talking about. So let's look at an example. Let's say that we have a person, an athlete, we're all athletes, right? Sitting in a locker room unclothed. The walls are at a temperature of 15 Celsius. Estimate how much cooling is taking place due to radiation. Now this is kind of an interesting problem. Okay, here is our person, our athlete. It's just an object. So here's the object. Two things are going on here. The person is radiating heat away. They're radiating in the infrared. They're also absorbing in the infrared. So if if the walls are at the same temperature you're at, then it balances out. But if the walls are much colder and they're not radiating, then you're going to be radiating your energy away, but it's not going to be coming back to you. So what we can do is we can calculate both of those effects. Here is the person's radiation going out. They said the person's emissivity is 0.7. Here is the Stefan-Boltzmann constant. They said the surface area of the person is 1.5 square meters, and they suggested the person's surface temperature is 307. So putting all those numbers in, it says this person is radiating at 529 watts. 529 watts, joules per second, are radiating away from this person. Now that's going to add up. That's going to be pretty significant. If you're sitting in a room where you're radiating all this energy and nothing's coming back, you're going to cool down pretty quick. Now, fortunately, the room's not at absolute zero, and so we can also calculate the rate of energy coming back. Now, for the energy coming back, we get to use the same emissivity constant. So the absorption constant matches the emissivity. This is energy being absorbed by this person. 0.70, same, so this stuff's all the same. The only thing different is the temperature. Now, this has to be adjusted so that it's in kelvins, and I did that. So what we've got now is the person is radiating away 529 joules per second, and they're absorbing 410 joules per second from their environment. So there's still a net loss every second of 119. Now, I'm guessing you guys have maybe experienced this. If you ever come home after a vacation, maybe the furnace was turned off, it's cold weather, and you walk in a house and you go, this room just feels cold. And it's not so much the air in the room, okay? The air is not necessarily the major factor here. It's that literally the walls are cold and they're not returning much in terms of radiation. You're not picking up that radiation. And when you turn the furnace on and the air starts to heat up, you go, well, the air feels warm, but the walls still feel cold. It's literally what's going on. Until there's enough time for the walls to get back up to the temperature you're used to, you're not getting that radiation effect. Okay, and it turns out the radiation effect is pretty important. Another way this works is for the object. Let's imagine this is a car sitting out on the street at night. Now, what happens to a car sitting out at the street at night is it radiates. The car radiates energy away. Now, even if the air temperature is not freezing, let's say the air is, temperature of the air is 35 or 36, 37 degrees, it's not freezing. Air is not a very good conductor. So air is not very good at transferring energy to your car. And that means that the upward facing surfaces of your car, the roof and such, the ones that are radiating away, they're not getting much back if it's clear skies. So if it's clear skies outside, the car's parked outside, it's not super cold, 37, 38 degrees, you could still have frost in the morning because the car, through radiative losses, will actually drop below the temperature of the surrounding air. The air around it cannot transfer energy fast. It's not a very good transfer of energy to keep the car at temperature. So that's always an interesting effect when you walk up and the top of the roof is, you know, crusted with ice. Sides of the car are fine. Why are the sides of the car fine? Because there's other things surrounding the car that radiate back to the sides, but there's not much that radiates back to the roof. Okay? Interesting radiative effect. Okay, here's a person sitting out in the sun, and it's saying, hey, if you want to get the full effect, rather than this person, maybe you want this to be a solar panel. So you want to tip your solar panels up so that they are making full use of the light coming in. This effect that we just looked at in the previous one is what gives us the seasons, right? Earth has seasons. Here is the sun. This is not to scale here. But as the Earth is orbiting the sun, the axis of rotation continues to point in the same direction, close to where the North Star is, just by coincidence. But notice that the axis continues to point in the same direction. That means the most direct sunlight reaches the Earth during this, in the northern hemisphere, during this part of the orbit. And the most direct sunlight reaches the southern part. So this is what it looks like, summer for the northern hemisphere, and this looks like summer for the southern hemisphere. Okay, that cosine theta factor. So this past year, I actually had solar panels installed on my house, and I was fortunate enough, the engineer in charge of the project was good enough to work with me, and you can actually go through and use these formulas, kind of integrate, during the passage of the sun, during different times of the year, how far above the horizon is the sun, and then how much energy is available, and what's the best angles to tip your solar panels. Anyway, it was kind of a fun exercise in predicting, and now that a year has passed, I can kind of see that it panned out. It's about what was predicted, about what those formulas suggested we should have during different times of the year. That's what we've actually ended up with. All right, here is some thermograms just showing that you can look at heat coming off, physiologic heat, to look for circulation. Okay, maybe one last example here. I think we have a couple minutes. Let's apply this to a couple of different stars. So in astronomy, when you look at the stars, and you hear these crazy things, right? Like that star is 1,000,000 times bigger than the sun, and that star has a surface temperature, of how do we possibly know these things? And it's by analyzing information about the stars. We can get surface temperature by looking at the stars. So our star, the sun, is, you can look at its spectrum of light, and you can match that up with a temperature of about 5,800 kelvins. And so let me go ahead and move on to this next diagram. So we're comparing the sun with the red giant Betelgeuse, which maybe you've heard of, maybe not. It's in the constellation Orion, very prominent star. Now, by spectral analysis, by looking at the light, the sun's kind of a yellow-white star, and we can identify that as 5,800 Kelvin. We have not taken a thermometer up and put it in the sun. We look at the light being generated, and that tells us the temperature. Now, Betelgeuse is red, and we can match that up with a temperature of 2,900 Kelvin, so about half. And those are in absolute temperatures. Now what we can do is we can use ratios. What we can do is say that the total power output of Betelgeuse is going to depend on, now this right here is the emissivity, here is the Stefan Boltzmann constant, here is the surface area of the star. So I'm writing down that formula of dQ/dt, and dQ/dt is power, right? If I do a heat rate, any kind of an energy rate can be thought of as a power. So this power is the total rate of energy coming off each of these stars. Now when I do a ratio, the emissivities cancel out. Stars are typically have emissivities of about 1. So the material, the low density gas material in the outer layers of a star are really good at absorbing and really good at emitting light. The Stefan Boltzmann's constant cancel out. The 4 pi's in the surface area cancel out. So we're left with a ratio of radiuses squared and temperatures to the 4th power. So again, I'm going to use a ratio approach here. They said use this information to determine what the diameter, how the diameters compare, how the radiuses compare. And so I've just been careful with the ratio formula and solved that for RB. And when I did that, it told me in the problem that Betelgeuse produces 10,000 times as much energy as the sun. Now that, we actually have to be able to determine how far away it is. So there's a parallax method. We can determine how far it is away, and then we can measure its total brightness, and that'll tell us the actual amount of power. So Betelgeuse is putting out about 10,000 times as much energy, and I put those ratios in. Turns out that Betelgeuse has 400 times the radius of the sun, or equivalently, we could say diameter. So Betelgeuse is 400 times the diameter of the sun. That's the diameter. If I think in terms of volume, that would be 400 cubed. That's 64 million times the volume. Now, the radius of Betelgeuse, if I put numbers in, works out to be 2.8 10 to the 11 meters, and that would extend out past Mars' orbit. So now it's not it's a red giant. It's a later stage in star development. The material that the star is made out of has spread out. The sun also will go through a red giant stage. It won't be as large as Betelgeuse. It probably will extend not much past Earth's orbit. But anyway, this is a way to go in and actually determine, and this was astounding, you know, when astronomers, astrophysicists started looking at stars and analyzing their properties, they realized the size of some of these stars is just enormous, which means that the material has spread out over an enormous distance. Okay. All right, I think that's it. I think that wraps this up. Yeah, we're just into the summary. So, all right, chapter 19. I'm a little worried. There's so much stuff in there, but I think we got through fine. Ooh, that last statement, the radiation, light, radio, microwave, infrared, it's the whole spectrum of light that can be considered when we're looking at radiation effects. All right, I think we'll stop there for the day.